The plane waves are a solution that works in the wave equation. And there's other kinds of solutions, like waves emanating out from a point, and you solve them in spherical coordinates. But plane waves are pretty good, even looking at spherical wave fronts that came really from far off, where the surfaces are almost planar. Okay, and so they're very handy. They're complicated enough, and we talked about one that was just moving along the z direction last time, and that's fine. You can always look at a plane wave and rotate your whole coordinate system around so it's moving along z and write it as a sine or a cosine. And that's nice until you have a boundary between different materials. So here we've got material 1, mu1, epsilon 1, and material 2, mu2, epsilon 2. And we're talking about dielectric materials that don't have conductivity in the rest of this. And it's complicated enough. Now we have to define, we're kind of stuck with if the wave is traveling off in nice z or y or x-axis, it could be coming in at this angle. Coming in like this, and in this boundary, I'm trying to draw a direction to it. Okay, and so it can have, and this is the propagation direction, not the direction of the electric field. It turns out the direction of the field is always perpendicular to the direction of travel. The systems that we're looking at. Okay, so we can have an electric field pointing perpendicular anywhere along this line, coming right out at you, or have some component like this. It's always got to have a 90-degree angle. And we can map that on to what we've already been thinking about for plane waves, where we're drawing the sinusoid and going, yeah, we're going to have these amplitudes, and it's going to be modulated by the sine waves. They're going negative, they're going positive, they're always going perpendicular to the direction of travel of this thing. Direction of propagation. Okay. So we'll knock that out. I'm going to have to erase a little bit so we can see what's going on. So this k vector, okay, what we used to have, we didn't really think of as a k vector. We've got the magnitude of k right here now. I need to start being careful about that. K vector is going to be this k magnitude, and so maybe I'll draw k with a vector over it. Some constants times the frequency, and it's a little redundant, but propagation direction, propagation unit vector. So now it's called a wave vector. And it's wave number times a unit vector along this direction. Okay. And I think in the book they call it a sub k. We'll do that. A sub k. Just to disambiguate. Okay, so this thing comes in here, and it's this magnitude of this thing. Okay. And the reason we want to write that thing out as a vector is so that when we're working with this complex exponential, we love that it works with the wave equation. It's really easy to take both spatial and time derivatives, and we want to keep that. So all we have to do to make that work in something a little more complicated that has multiple components to its direction is put that wave number, do a dot product with our position in space. Okay, so we used to have, and then something reassuring is we can get back our previous solution. So if the wave vector is going to be k times z hat, in a special case, E is going to be E naught. Now I've still got my vector, I've got my direction for E. That's the stuff I was talking about. Is it pointed out at you? Is it this way? But the envelope that's multiplying it is going to be e to the j. And now I've got this special case, kz dot my position vector. Okay, a little r. And let me knock out some of this stuff. Wave vector is this thing, minus omega t. And in Cartesian, R is x hat plus y hat plus z hat. Okay, I'm getting into chapter 10 if you're following along in the book. So when I do this dot product in this special case, I'm going to get k z hat dot z hat. These dot products aren't going to contribute because I'm dotting with z hat. So I'm going to get back kz minus omega t. What we were talking about before. So we threw the sine wave at you, but behind the scenes it has all these other abilities that can go in different directions by turning this wave number into the wave vector. Okay. What are we going to do with this? Okay. I'm going to think about what happens when we have a wave incident on a surface at some angle of incidence. We're going to get a reflected wave coming out this way, and you've probably seen this before in an earlier physics class. You're going to get a transmitted wave. Maybe sometimes the amplitude of these things are going to be 0. We have to do some stuff to find out transmitted wave. And all these analyses, we look at what's happening right here at the interface because we have knowledge of those boundary conditions. We worked hard to get that tangential component is continuous. Okay, so what we have to do to figure out what the tangential component is on this side of the material, compared to this side of the material, we'll look at the total electric field on just on this side of the material. It's going to be E material 1, and it's got both the normal and the tangential component still wrapped up in it. E incident plus E reflected at z equals 0. Z equals 0. And of course, at the same time, might as well say t equals 0. On the other side of the boundary, material 2, we just have that transmitted wave. At z equals 0. Okay, so we're talking about right here, matching those things up. We can split these out into their tangential and normal components. And we can do that EI is EI tangential plus EI normal. And remember, these are the amplitudes multiplying the sine wave or the oscillatory function. So they're constants, they're kind of fixed. The amplitude of this envelope, wherever it gets to its maximum, is the same. It's a really uniform sine wave doing this, and that's because we don't have any conductivity, and conductivity represents losses in a material by driving currents in it and heating things up. Okay, so these amplitudes are staying constant, and that's this. It's not going to change. So we got the tangential and normal components, and I can break that down here. Tangential and normal components of, here's your E, if we've got a wave that's doing this, It's got a part that's along the surface, so that's E tangential, and it's got a normal part. And then they're multiplying that whole thing by this complex exponential. E to this thing up here. J, wave vector. What do I have? Well, let's just stick into the XZ plane. We've taken everything and flipped it around so that this thing is planar, and call that x-axis. K dot x hat, K dot R is what I'm trying to write. Plus z hat, but z is 0 when I'm at the interface. Minus omega T. Okay, and I haven't quite figured out the total electric field on this side because I've also got to add this reflected field. Okay, so if I'm doing total field on side 1 of the boundary, okay, total field on side 1, it's a little bit goofy looking right there, but it says total field on side 1 of this boundary. I'm going to add in the reflected component, and it's got its own tangential and normal components, but those are fixed at whatever this wave started doing. It's doing something like this. This direction is set. Okay, by rules that we're about to find out. E reflected tangential plus E reflected normal e to the j k, and I need to start adding some subscripts. It's getting a little bit tiny, but k depends on the material property, so I need to have k1 on this side of the boundary, k2 on this side, so I can group that up here, k1, k2. Okay, I'm going to erase some of these, and I'm focusing on this incident, reflected, and transmitted picture. K1 dot x hat. A lot of little tiny stuff. On the other side of the boundary, okay, we're going to stay at z equals 0. We're getting bigger z. We're getting farther away from the boundary. Z equals 0. We're going to write out our expression for this transmitted wave. It's doing that. It's got some tangential and some normal components. And it's multiplied by this oscillating complex exponential. On side 2, E reflected tangential plus E transmitted tangential. Oh no, identical subscripts. Transmitted tangential. I'll read them out loud. We're going to ditch them pretty soon. E transmitted normal. That little part right there. And this little E that I've tried to draw perpendicular. This component of this vector is perpendicular to this boundary. This one is the tangential part. And those are just constant amplitudes. E to the j k2. I'm in material 2. Dot. And I don't know what angle I'm going at. We need to leave that. X hat. I'm at z equals 0. Oh yeah, I gotta leave my minus and mega t's in here. Okay, so sticking all that stuff together. The only way we can match up these tangential components is if all these oscillatory terms match up. Then we can divide them out of the equation. Okay, and we're going to let these amplitudes, and this incident wave, we're setting that amplitude, and then these we're going to have to let come out of the equation. You know, what are those amplitudes? But what we get out of this is these, because we could be at any value of x, we could move this up here, we can move it down there. The picture should look the same. So these k's sub x's anyway, have got to be the same. If we come out in y, it's a fairly uniform looking thing. K sub y has got to be the same. Okay. All these k's come out to be, so it's called phase continuity. And the same thing here, it's got to work at any time, so we have to have the same frequency across all 3. So I'm going to erase this. I said I was going to ditch all these subscripts. The only thing we're really going to take home here is that oscillatory term only makes the boundary conditions work if it's the same for all 3 terms. It can be divided out. And from that, we're getting kx1, okay, k sub x incident, and then material 1 kx reflected is kx transmitted. Omega 1, omega incident is omega reflected is omega transmitted. Same frequency. Okay. So this is all for phase continuity. And we had to have that to make the tangential components continuous across the boundary. What do we get out of that? Let's take apart these wave vectors, and it's done in chapter 10. We're in